Hello and welcome. In this talk, I will be presenting a reinforcement learning approach to solve a very popular and widely used control technique, namely the LQR technique. So I will start by looking at what is the LQR problem. So in the LQR problem, we have a model of the system. Okay? That's the basis for this LQR design. And in this model, we have the states X and the inputs U. And the objective is to find the control input or the control policy that will minimize this quadratic cost function. This is where the name LQR comes from, partly because we start with the linear model and we have this quadratic cost in the states and inputs. So there's a couple of ways in which we can get to the solution. One is using the method of Lagrange multipliers, or the other way is using dynamic programming and Bellman's optimality principle. So the end result is that we get a controller in this form. So basically what it is that we start by obtaining the solution to this Riccati equation that depends on the plan's parameters and the weighting matrices. And from that Riccati equation, we plug it into this formula to get the controller gain. So the key usefulness of this result is that we can get a closed form solution and it can be computed online or offline. The other thing is that it's very easy to implement because at the end, it's a simple gain. And it also has good stability margin properties. So let's look at this using an example. So here I have an unstable system. Xk plus 1 is 2xk plus uk. And I start with the initial value 1 and I simulate it and I see, of course, it blows up. Now I specify a cost function, which is just x squared plus uk squared for an infinite horizon. And I'm trying to get the control input u that will minimize that. So, I use the function LQR regulator gains to compute that gain kappa. And once I compute that, I plug it back into the system that I had. So U is negative kappa X plus some exogenous input, typically it's 0. And here I set V to be some random input. And I see that with that stabilizing gain, the system actually does not blow up. Okay, this randomness is because I gave a random input. To do an apples to apples comparison, I should actually make it 0 and then simulate it. Let's see. Okay, we were here. And I was just trying to show that how we compute a stabilizing gain and the system, and we get, and the LQR gains actually stabilizes it. So to go to the summary, so it's based on a linear model and a quadratic cost, and the LQR gives a closed form stabilizing solution. Okay, let's, now we want to do the same thing using reinforcement learning. And the difference here is we don't have a model of the plant. We keep the same cost function, and we now want to compute the control policy without knowledge of what this system is. Okay, so we start by defining what's called the value function of a state X, okay, given that we use an optimal policy UK. So this is the cost that is accrued from that state to the end of the horizon. So we take that cost function and just plug in this policy that we're using, and that is the value function. So this concept is also there in control theory from the beginning, and it's called the optimal cost to go. And when the system is linear, this value function takes this form. It's quadratic in the states, and this XR is actually the solution of the Riccati equation. So we will use this result a little further down in just a bit. So the other concept we are going to use is the action value function, or the Q function. This is the cost that is accrued from a state and action state xk and action uk, and then after we just have some policy uk at state xk, and after that we use the optimal policy uk is minus kappa xk. Okay, so if you look at this relationship, we see that the q function is actually satisfies this recursive equation, because these infinite terms, this infinite sum is actually the q function starting from xk plus 1 with the control input minus kappa xk plus 1. Okay. The other thing is that the q function is also related to the value function, because in the q function, if you use the input minus kappa x, you get back the value function. So we can put these two together and write this result that relates the q function and the value function. So we have used two properties of the q function. One is that it's recursive, and it's also related to the value function. Okay, so let's start with that result, that the q function is related to the value function. And for now, let's assume that the system dynamics are known and it's linear, and see where it will lead us. Okay, so if the system dynamics is linear, then from control theory, we know that the value function is related to the states at xk plus 1 through this relationship where xr is the Riccati equation. And because we also assume that we know the model of the system, this xk plus 1 can be written in terms of the previous state and input. And we expand this out and get this result for the q function, which is quadratic in xk and uk. And then if you try to minimize u, we get back the solution we got from LQR. Okay, but yeah, so then we are back to square one. Basically means if you know all these parameters, then we can compute the control input. But what this told us is that this q function has this particular form where it's quadratic in x and u, and then there is this matrix inside, which we call the kernel matrix, which is symmetric. So based on this insight, we write the q function as this unknown S matrix, this unknown S in terms of this unknown S matrix. And then if we expand it, we can see that the q function is actually linear in the entries of that S matrix and quadratic in x and u. So then based on this, if you try to minimize u, the result we get that is that if we know this kernel matrix, then we can compute u. Okay, so let's see how to do that. So the reason we went to this exercise is to see that the q function can be written as a quadratic quadratic expression in x and u, and then a linear thing in the kernel, the entries of the kernel matrix. Okay, so to start that, we write this recursive relationship for the q function. This I just rearrange it. I bring the q function here to the left hand side, and then write the q function as that quadratic term in xk and uk and the linear term in s. And this is the fundamental equation that we are going to use to actually compute the control policy, because once we know the s, we can then compute u using that. So how we do this is we start at a particular state and apply a control input, and then the system reaches a new state xk plus 1. So then we know all the terms in this equation. We know xk, uk, xk plus 1. Well, we start with, and we also start with an initial assumption for what our kappa is, or the gain is. And all the terms here are the weighting matrices. And once we have made sufficient number of these observations, we can then estimate, compute the values of S, and from that estimate what U should be. So in summary, this is a model-free approach, but it assumes the model linearity, and it uses the quadratic cost, and this is an iterative procedure to get to the control gain. Okay, so this has been implemented in two functions. One is regulator gain. I basically went over the regulator method in the previous slide. The tracker is almost similar. It just has what's called the augmented states instead of the states of the system. And this is the usage syntax. It's just like the other design functions. We can, this LQ regulator gain, we give the specifications of the environment and the weights and the time specification. And we need an initial estimate of what that controller gain is. If it's not given, it's assumed to be 0. So where this method expands the previous approach is in the environments that can be specified, because it really doesn't need to know the internals of what's in the environment. Of course, it accepts all the models that the control functions supported earlier. But the difference is, even if you give one of these, it's not looking into the internals of what's in this model. It's just simulating them and with an input, looking at the result and using that as a basis to compute the controller. But you can give any of these, you can give a function or a compile function. You can give any general function, or you can interact with the device. We are still working on this. We are adding more environments that we can support. So let's look at a basic example. So here I have a single state, single input system. It's just given as a function. And this is a simulation of it. And this is how this function, it's simulating and computing the controller. So I specify the environment, the input model is that function, and I start at a value 2, and then we design the controller. So I've given the weights to be, again, like before, the same weights, Q and R are 1 and 1, and I simulate it for 25 time instance. Okay, once we get that controller data object, I can get a whole slew of properties. Like, yeah, so the batch length, that is how many simulations it did before it computed a controller. Okay, whether it converged, yeah, this is the same data object. Feedback gains, yeah, so that's the I think the most important one. What was the feedback gains that were computed? And we can query that and see that this is the value we got, and it actually agrees with the results from LQ regulator gains. Okay, then we can plot the gain values. We can see how it reached that value. Yeah, this is the batch length. Yeah, so here we can see what were the feedback input values that were used. What input the algorithm was pinging the system and getting its responses. And this is the actual state of the actual trajectory of the system. Starting from state X, it reached its final destination. Okay, so let's look at some more examples. Okay, so here it's more general. I've shown how to interact with like a foreign function. So I have this very bare bones C code, which I then compile and create this library. Okay, so we can start. So you can use this as a basis, or this as the environment for this function. So I use the function foreign function load to load that function from this library, and I need to specify what are its arguments. Okay, so, and once I get that, I can give that as the input model. Okay, that as the input model. Yeah, it also needs to know how many outputs, because that's the first argument. And then I start with an initial state of -1. And then I have the same weights and simulate it for 40 time instance. And here we can see how the feedback gain values finally converge to their final value. So the other example I'm showing here is with tracking. I did not really go fully behind the theory behind this, but it is almost similar to the regulator problem, except that the states are just not the states of the plant, or the environment. The states are also this come from this track signal. So it actually augments them. But once we augment them, then it's the same thing as before. And the function also is the same as the regulator function. We have the environment. We give a bunch of weights. We give the bunch of weights. Here I've given an initial estimate for the controller, and then I simulate it for 75 time instances. And you can see that it finally converges to the target value that was set. Okay. All right, so there are some limitations in this approach too. So the key one is that, let's go with this example. So I have a function here, but if I give a gain here of 2, this will cause the system to blow up. So once things blow up, then everything just falls apart. So it's very important that that initializing gain should stabilize the system. Okay, so with that we get these, the system just blows up. So that choice of initial gain is very important. And once we give that initial gain correctly, then we see that in fact the system regulates it and brings it back to the origin. So for unstable systems, this problem is even more exacerbated, because it's going to blow up. So it's very important that we give a good enough gain so that the system does not blow up. Okay, so when we try here, I've tried with some gains and it did not converge to the optimal solution. So then I adjusted the gains and got it back to what the actual results should be. The same thing for systems with disturbances. It's important that you see there's a system and I gave it some random disturbance, and with an initial gain of 0, it did not converge to the optimal gain. Again, we have to adjust the initial gain to get it to converge to the actual value. So this is a key thing here, that that initial gain that we start with is important. So to summarize this whole thing, this is an iterative method to compute a controller without any knowledge of the system's dynamics. The controller simultaneously regulates and converges to the optimal gain. So it's both learning and stabilizing the system. So there are some limitations. One of the limitations is, although it doesn't know the system dynamics, it assumes that system dynamics is linear. And the other thing, as I showed, was that we need to start with a stabilizing gain, especially for unstable systems, for the system to actually converge to the solutions. So there are some additional resources too, and this is a community post I wrote about this. So with that, I will wrap up my talk. Thank you very much for your time and attention. If there are any questions, I look forward to answering them.